Good day, everyone. Thank you for joining this webinar presentation. My name is Philip Payne. I'm actually the technical lead for the Cybersecurity and Information Systems Information Analysis Center. Um, I am taking over for John Clements, who is normally the lead for the HDIAC, or the Homeland Defense and Security Information Analysis Center. John is actually at the National Homeland Security Conference in Cleveland, Ohio, so I'm just taking over to host for you guys this month. CSIAC, along with HDIAC, are one of the three IAC domains under the DoD Information Analysis Centers operating under the Defense Technical Information Center, or DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. HDIAC serves as one of the premier information research partners and curators of technology advancements and trends for the Homeland Defense and Homeland Security communities. As such, our organization supports those working in the Homeland Defense and Security domain of DoD research and engineering. We do this by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. We provide research and analysis services and help unlock access to information, knowledge, and best practices from the government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar and that it serves as a catalyst for community collaboration and improved DoD Homeland Defense and Security research. Before we get started today, I would like to note a couple of administrative items. First, if you're dialed in by phone and would like a copy of the slides, they were posted to the HDIAC webinar announcement. You can go to HDIAC/webinars and find today's webinar. When you click on it at the bottom of the announcement, it will say to view webinar PDF, click here. Second, all participants are muted, but feel free to chat using the attendee chat button on the left-hand side of the webinar screen. You can use that chat to chat with each other, and I'll be monitoring that chat during the webinar. However, if you'd like to pose a question for the Q&A session at the end, please use the audience questions tool, which is at the top center of your screen. It's the little icon that looks like a chat bubble next to the file folder. At the end of the presentation, I'll go over the Q&A. For the benefit of those on the phone, I'll read those questions out loud to the presenter. If you have any technical issues during the presentation, have no fear. The full presentation will be available online. Check back on the HDIAC website. Once the webinar is posted, the GoToWebinar button will take you to the YouTube link. And with that said, I'll pass it off to today's presenter. Thank you.
Thank you, Philip. My name is Craig Rieger, and as part of my research that led to, in part, the Master State Awareness Estimator, I've been working in the area of resilient control systems since the area was pioneered by Idaho National Laboratory, along with our collaborators, which we had a nine university NDA back in roughly 2008. We also have Resilience Week, which covers more than just resilient control systems and other ideas. And the reason I mention that is mostly because this is a broad area of research, and a lot of it's still new. You still see people that are sharing definitions in resilience depending upon their domain, but ultimately it's really what we're after. And so if you think about resilience and the difference between it and reliability, is part of the precursors of Resilience Week. That was one of the first questions we discussed. Okay, what's different between reliability and resilience? And so we have a definition for resilient control systems, which I won't share with you, but ultimately, a lot of it relates to what some people may question is the right term, but the unexpected. And it's not always necessarily the damaging storms, which the natural is part of the mainstream definitions, or man-made, such as cyberattack, which also could include human error, those people that are working for you making mistakes. The context is still, you may choose a different term, but how do you deal with the unexpected? And really, you may not necessarily be able to harden everything, nor are you able to necessarily, and it may just be an expense, but you don't necessarily know how things are going to hit you. So from a cyber attack perspective, from a mistake or misoperations, as they talk about in the power system world perspective, the first thing you really need to do, and what we set out to do within the area of resilient control systems, is understanding the state awareness. So noting that situational awareness is a broadly used term, not just in DoD and elsewhere. One might ask, what's the difference? Well, you might have many situations that you're looking at the state to give you information on responding to that situation. But state for us is just what it says. What is the state of the system? You need to have that information to be able to fully characterize the decision space that goes with it, whether it's a cyber attack, whether it's some physical failure, whether it's some misoperations, somebody did something they weren't supposed to do. The responses to that are going to be different depending upon what it is. And current control systems today really don't have any awareness of cyber. There currently are many cyber teams, of course, that are supporting mainstream industries to set up the right perimeter protection, sensing, potentially, and other things like that. But there is no awareness necessarily within the context of those people that are running the system. And I mean those people that are running the physical system, the power system. What could be happening in the cyber world? And it's very important. And we believe the future is really to inform that discipline, but also to create a cross-disciplinary interaction. So the physical folks may not really understand IP addresses, but if you tell them a certain part of their system, a physical system, is affected, that makes sense. On the cyber side, they don't necessarily understand what's consequential on the physical side, but if you give them a perspective of what's important on the physical side, and as a partnership, look at the communications, et cetera, that are affecting that, then you start understanding how you're looking to develop this team relationship. And you very much need this team relationship. So the Master State Awareness Estimator, MSE, is just one of actually several projects and technologies, including provisional and patent applications, et cetera, that or awarded patents that are out there that we've developed at INL, but in collaboration with others. And in part, it's really looking to do that. It's looking to provide that kind of information perspective of what happened. Is it cyber? Is it just a physical, which could actually be physical security issues too, but for us, more importantly, the benign aspects of misoperations and things like that. What ultimately is it? And providing some indication that's at least simple to understand of what's going wrong. We actually have other projects that get into more down in the weeds analytics to provide supporting evidence for what has happened. And so characterizing that type of thing, but also distributing it. So centralized control systems is something I've been involved in since the beginning of my career. Understand the need for centralized control room. The challenge is in contested space. So if you're working in contested space, what happens if you lose connections to the field from some things? Wouldn't it be better to consider distributed understanding of the system, that instead of top down, in other words, everything comes to a centralized computer and that's where the understanding is? What about bottom up? So you could lose some of that communications, but it could be organically redeveloped through something like a distributed state estimator. And so in the case of MSE, we actually have two different parts. There's something that is looking at the network traffic side. So your supervisory control and data acquisition system is communicating, they are distributed. We're looking at that in the substation, and we have a machine learning look at that. And then on the physical side, we've got a distributed state estimator, and it's actually a two-tier estimator. In other words, there is a substation, distributed decentralized estimator, and then there's also a centralized estimator that aggregates the information from the individuals. And the point is that you can do that bottom-up approach that I just mentioned. You can organically recreate the system. We're in contested space, security isn't perfect. How do we understand it? How do we build systems that are inherently resilient so you can't compromise everything? And here again, that's really what the MSE is about. So we have the network analysis, that is a machine learning cyber sensor. We have the state estimation, which is a distributed state estimator, but also has independent synchrophasers that it's looking at for information to complement it. And then ultimately, depending upon what alerts are seen, we present that to the operator. And whether it's a individual line drawings for a distribution system or whatever, the point is you've got two parts of the triad. The left part is about state estimator alerts, and the right part is about the network alerts. In other work that we're doing, we also use the bottom part of the triad, which talks towards resilience. So irrespective of the root cause on the left or the right, what is the impact to my system? We didn't do that in this particular work because we're looking specifically at substations and how we can do a more comprehensive analysis of what's going on that takes the benefit, here again, of what's going on in the physical system world as well as what's going on in the network world. And so in doing so, and having the system as an out-of-band system like you would do with a security system, the intent would be to have an integrated analysis that can tell the dispatcher, the power engineer, and yes, even the cyber defender working in collaboration, what the problems are. So from a relevance to this, we looked at several different scenarios, and we developed our own for the point of view of a storyline. We took the role of developing a not notional company, High Salt Energy, actually supports mining and other things in the industry because, of course, when you're starting to talk about scenarios, you don't want to use real names out there, and that's really not the purpose. The purpose is for us to talk more in terms of, okay, what happened? What things are relevant? As you can imagine, in this world, if you're starting to consider the cyber and physical scenarios that we took, and we just took a snippet of representative kinds of scenarios in both the cyber and the physical world, you could have a number of others, but we wanted representative ones. From the cyber side, though, you have people that leave not necessarily happy, depending upon how good you are at removing their logins and other things, assuming they didn't put some kind of backdoor, etc. You may or may not be in a position of concern. And so in the scenario relevance that we're talking about here, you have a disgruntled engineer. Could be that individual does something before they leave or just after because you haven't scrubbed the system of what they've done. Relative to the physical side, you could have a transmission system that was affected by some kind of a forest fire or something that requires rerouting of the power. You may not have the line capacity to do that, but the intent here is that a situation has occurred that's requiring you to make that shift, to make that change. And therefore some kind of manipulation of the system into non-ideal circumstances could occur. Recognizing that at the substation level becomes very much then important. But even looking at the physical scenarios, as you will see, you may also get reinforcement of something that might be cyber related. So from a cyber scenario standpoint, we looked at, in particular, three types of issues or scenarios, if you want to call them attacks. The first of those is a data injection attack. In this case, that's not changing necessarily packet data, but changing settings. So as you can see from the figures on the right, there's a number of different types of control system components that have lots of configuration settings. Those people that work in the control system world get it. There's lots there. In the power system world, relays and things like that are extremely important to ensuring protection of the lines and other power assets going forward. Well, those things could be changed. Recognizing those kinds of things that could be changed is very important. We could recognize that through the network. We can recognize that through potentially traditional logs. In our case, we're looking to keep ourselves away from log evaluation. A current IDS can actually evaluate some of the logs. Control systems have that logs in limited fashion, but we don't want to be dependent upon those in the field. We want to look at network behaviors in particular from the cyber side. And so the detecting a failed login attempt then becomes very important. Here again, we're not dependent upon logs and how we've looked at it with our algorithms. And then denial of service. And denial of service may or may not have a major impact. It depends upon the limiting timescale of the operation. So if you slow down the traffic, is there some kind of logic that expects that information in a certain time, or if its all becomes unstable, etc. The point is to recognize any kind of latency that could be characteristic of something malicious. And so that's very important to us. On the physical test scenario side, just kind of aligning this with what we talked about as current transformer, you could be recognizing that also from the state estimator side. So if you're seeing synchrophasor data coupled with the model that's telling you that something isn't right with the field that relates to the relay, that becomes a reinforcement of, if you've got also the cyber that's saying something that's going on the network, that you can use to make a judgment, to more fully characterize what the root cause is. The other thing that we've got in the state estimator is to recognize things that are changing in the environment. So load and generation changes. We have the voltage magnitudes, angles, power flows, etc. Okay, we're seeing this change. Why are we seeing this change? Was it an expected change? And we're just having a confirmation. Also topologies. So in our case, you could switch between different sets of two radials to have a resulting different topology, different power flows, and we look to recognize that.
We will now demonstrate 3 cyber sensing scenarios using a record.
So just to kind of conclude what I was looking to say on this thing, we looked at this in from 2 perspectives, or from 2 scales of testing. The first scale of testing was actually in hardware in the loop using real systems, some of which you saw in the pictures. And then a test on the INL test site. So the INL test site has different distribution level voltages and equipment, and we even added some additional interfaces to that allowed us to test between a couple of substations. And so, the benefit of having that kind of infrastructure is it allows you to actually do more full-scale testing, but a lot of it was started in hardware in the loop. And so in what we're going to be looking at in the next 2 slides, we're stepping through some of the testing that was done, and you will see reflection on the triad, etc., like I've talked about before. We'll start with the cyber scenarios and then go to the physical scenarios that we just talked about, and you can see them working through in the demonstration.
We will now demonstrate 3 cyber sensing scenarios using a representation of a substation at an INL test site. A more complete description of the system topology will take place during the physical scenarios. In this first test, we are demonstrating the MSE's capability of detecting and alerting to a false data injection scenario simulated by a CT ratio settings change to a relay in the system. On the right, you can see a remote terminal accessing the relay and performing the settings change. In response to this settings change, the The MSE is able to monitor the communication between the devices and detect the anomalous condition, alerting the HMI on the cyber portion of the triad at the relay. In this next scenario, we are demonstrating the MSE's capability of detecting and alerting to a failed login attempt to a device in the system. On the right, you will see our remote terminal attempting to access and log into a relay on the system. After 3 failed login attempts, the relay refuses connection over the network, and the MSE is able to report the anomaly to the HMI, creating an alarm condition on the cyber portion of the triad at the relay. This event will also appear in the alarm summary of the HMI for an operator to view, including the alarm message, timestamp, and affected devices. In this final scenario, we are demonstrating the MSE's capability of detecting and alerting to a denial of service attack on the system. We are using a Raspberry Pi to emulate an attack targeted to a device on the network. On the right, you will see our Raspberry Pi initiate a packet flood attack to the relay. The MSE detects the anomaly and alerts the HMI to the cyber attack taking place on the network. This alert is shown at the top of the HMI, indicating a system-wide alert, as opposed to a device-specific alert shown in the previous examples. As with the previous example, the alert can be found in the alarm summary for an operator to review with relevant alert information.
Now the physical scenarios.
We will now run through several physical scenarios. These scenarios are performed on a real-time simulator model of a physical system at the Idaho National Laboratory. Although we are demonstrating this on a distribution system, this approach will scale to larger transmission systems. This system has 3 substations. The station at the top is a generating station, or it could be viewed as a connection to a larger system. We have several transmission lines that are connecting this system together, and we have 2 substations with loads. The station at the right has a single load and a single transformer, and we have voltage and current monitoring points at various points in the substation. The station at the left has 2 transformers and 2 loads. A bus tiebreaker is installed between the 2 loads, and that is supposed to be normally open in operation for this system. Again, we have measurements at several points in the system. The distributed state estimator used in this project has 2 levels. The Tier 1 estimator is executed at the substation level using local measurements. Separate calculations are performed on the low side and high side of the transformer to try to provide more granularity for detecting anomalies. This is able to handle much more complicated bus structures than are shown in this system in the HMI. The estimator is able to assess conditions and flag anomalies. These warnings about anomalies are sent to the Tier 2 estimator, as well as to a local HMI that can be looked at by personnel on site. The local estimators also clean up any anomalies in the measurements and send corrected data that goes to the Tier 2 estimator that does a system level snapshot to give a status of the whole system and also detect anomalies. In our first case, we're looking at a data injection attack. In this case, we have an incorrect measurement that shows up at this part of the system. We see the indication where we have a flashing red triangle in the left side of the triad indicating a physical alert. We can also look at the alarm message and see what caused this alert. In this case, the alert was due to the incorrect measurement. We can do a second attack at a different point in the system. Again, we can detect this attack with an incorrect measurement. We see an indication on the triad, and we also have an alert message that's generated. This approach can work with larger numbers of corrupted measurements. In cases where there is insufficient visibility to correct for these at the substation level because of the number of corrupted measurements, the Tier 2 estimator is also able to detect those anomalies. Our next scenario is a topology attack. In this case, the tiebreaker at the station on the left is still indicating that the tiebreaker is open and there is no current flow. However, an attacker has closed that breaker and has blocked those messages indicating the status change from going to the state estimator. The state estimator is still able to detect that there's been a change in the topology of the system and sends an alert warning. We have a message as well as the triad being enabled. The third test is a transient load change. This is meant to detect significant load changes, not small changes through routine operation of the system. In this case, we have a significant decrease in load at the station on the right. The state estimator generates an alarm and an alert message that can be reviewed if it's deemed necessary to do so. This distributed state estimator is not intended to replace the state estimator in the EMS system at the control center. This is an independent system to detect and locate anomalies due to cyber attacks or to misset equipment or malfunctioning sensors. It can also be used to provide an independent verification for the state estimator on the energy management system.
Alrighty, that concludes my presentation. I do want to mention one other thing, that there's a task force within IEEE PES that's been started to look even more broadly at the type of distributed cyber-physical sensing presentation or visualization of the information and how to do that appropriately, as well as what the responses are. And the responses are not necessarily physical, but they could be cyber. And where people think in terms of orchestration, what might the responses be? Might it be a software-defined network that closes off a external connection or protocol or some change at the firewall? So there's truly a cyber feedback loop in addition to the physical feedback loop that is all about, I believe, where the future is going. We need to let the individuals know what's going on, but to be very quick in response, we need to move towards things that can respond more and more towards autonomous response, I believe. We're a long ways from that, but we have to start somewhere. So thank you very much.
Thank you very much for that. We do have some audience questions, so we'll start there now. And our first question comes from Eric. He asks, what steps should we take today in the planning/programming phase of microgrid projects such as ERCIP project submissions to promote these capabilities in projects?
That's a really good question. And of course, what we're doing in developing some of these technologies, but then considering the future, the question is the differential, and how do we expedite them so that they're actually commercially available. I believe that the start of it is actually to take advantage of what we currently do know. There are intrusion detection systems that can be used within control system environments, but one of the challenges is that data goes to a specific security information event management. And so if you want to just look at near term, I believe there's ways we could leverage that, but also do some level of integrated visualization. Are the vendors doing that? Not to the way I'm aware, but at least you've got technology that's there with that information, and so doing combined databases. We've got other things that are being commercialized to try to expedite that, but I believe we're still a little ways off. But so the start is really to have the technologies that are there, and then start developing integrated ways of presenting that to the operators. And so to directly answer your question, I would talk about integrated cyber physical visualization, and what can be done to at least show like high priority alerts from a security standpoint, show that to the people on the physical side and do cross training as part of the new projects to ensure that what is presented is understandable on the physical side. And if you want to also show physical information to the cyber defender, a similar kind of training. Now, you're not going to want to send every alert from the security information event management over on the physical side, but perhaps the high priority. So even at that, there's going to be some development necessary. But if you're putting it in planning, programming, specifications, I believe that in part will start driving the vendors to do something in that area, as well as starting to bring in projects that are coming out of the labs and elsewhere that are already creating some of the building blocks for it.
Thank you. Our next question comes from David. He asks, does your model assume the presence of an independent communications network to facilitate bottom-up notification alerts?
Yes, that's generally what we are striving for. That doesn't mean that the same media can't be used for two different networks specifically, but we're looking for an independent network because we don't want what we're using to be independent to also be in fair alignment. And I mean, there's always a potential for that, but we're expecting it to be separate. So in the case of our testing, we actually had separate connections to a relay that had synchrophaser capability, or relays that had synchrophaser capabilities. But if you had a relay could still get compromised directly. So do you want a separate relay on a separate network? Traditional redundancy plays here. How much money do you want to spend is what it comes down to. Would it work? If you're talking about the state estimator model, would it work if it's all on the same network? Oh yeah. It's not a function issue. It's about protecting the independent analyzer from cyber attack itself.
Thank you. And as of right now, that's actually all the audience questions. Just listening to the presentation, this was very interesting. This was a great one for me to sit in, being the lead for CSI with the crossover into the cyber world. On the cyber side, we see a lot of talk now of mutual authentication and zero trust and optical physical diodes and cross-domain solutions and things like that. With the physical space related to these substations and ICS systems, obviously these are high availability systems. So I think your opening point about resiliency and redundancy really hits home, where we can't necessarily avoid to have a communication path down for long periods of time. So this was very interesting to me. I would like to thank Craig again for his presentation. And with that said, we did have one more audience question come in just now. And the question is, do you have any plan to incorporate a decentralized architecture into the MSE framework?
So the devil's in the details of what that individual is looking for. From a question standpoint, we believe we are decentralized, but we're at the behest of how they architect the power system. Specifically, or power, not the power system, but communications to the power system. So are they willing to put in independent networks and things like that? Our technology itself, it's built both on the cyber machine learning side as well as the state estimator. It is decentralized. It's built for bottom-up analysis. So you can do comparisons within the substation, but you can also do bottom-up indications. The presentation is distributed. So depending on the relay affected, even on the cyber side, we're hoping to get actually down to the individual IP, but if you have a denial of service on the whole substation, then you just have an overall alert. So everything we're doing is built upon being decentralized, but if you're talking about the communication systems, yeah, it's still at the behest of getting that set up in the substations in such a way that even that is decentralized. So segmentation and things like that to protect the system, those kinds of things would still come to bear. So hopefully I answered that.
And we had another question come in as well. Are you looking to continue the work with distributed ledger technology to trust the state estimations?
I guess I'm not familiar with distributed ledger necessarily. Blockchain? Okay.
Yeah.
That was the next thing I was going to say. And I believe I know this individual too. So we had not looked at blockchain specifically for the application here. That's just another enhancement of what we're considering. We were really more about the analytical solution and the presentation, but certainly to protect the system even beyond what the prior discussions have discussed. Blockchain could be definitely a characteristic of it, but we've not looked at that specifically.
Thank you. And monitoring the chat, I think that concludes our questions today. It was a great presentation. With that said, I'd like to thank our presenter for this month. John will be back next month to host. Hopefully I didn't do too bad of a job. But we'd like to thank everybody for participating this month. And hopefully we see you at our next webinar. Thank you.
Thank you.